Now, finally, we're going to do a little bit of calculus here. And I realize this may be ahead of where you are in calculus, but bear with me and get help if needed. You will get caught up pretty quickly. In the lecture that I posted on your website homepage, it actually shows you a whole lot more about the calculus that is required here and what integrals mean. Again, integrals are just areas under curves, but you're adding up a bunch of infinitesimal areas. So don't panic. You will get there. The physics is a little bit ahead of the calculus when we do integration, but it'll all make sense, I guarantee it, and I'll help you if you need it. What we're going to be talking about is it's a C-only topic, potential energy functions and forces, and we're going to have to use some calculus for this. So what we learned about before was that the change in the potential energy is going to be the negative work done by the conservative force. It's the opposite of the work done by the conservative force. You can think of it as kind of like putting money in the bank. If I put $100 in the bank, I've lost $100. That's negative $100 for me. But I can get it out of the bank again. The bank will give me $100. And now it's just like storing energy. And that's what it is. So the equation for the work done by the conservative force is this. The force dotted on the infinitesimal displacement. That is the work done by a force when it's displaced by an infinitesimal, super tiny distance. And what we do when we're taking the integral, again, it's the negative work done by the conservative force. When we integrate this, starting from x initial and ending at x final, all we're doing is we're finding the total area under the curve from x initial to x final. And this can be any curve like this. It could be some kind of crazy curve that's not a straight line. You could have something like this. Here's f and x. Your curve could be something like this. Could be something like this. Could be anything. And when we integrate, we're finding the area under this crazy curve from x initial right here to x final out here. That's all we're finding when we integrate this. So we'll get some more practice integrating, but I also wanted to show you how to find the force from the potential energy function. And that is, you do that by finding what is called the partial derivative. If you want to find the force in the x direction, you take the partial derivative, which here's the symbol for the partial derivative. You take the partial derivative, and this is called a round d. So it's negative, and that negative is from right up here. That's from the integration. It's the negative work. Work done by the conservative force is equal to the change of potential energy, and that's where this negative comes from. The force in the x direction is the negative partial derivative of the u function, whatever that is, with respect to x. So here's what this symbol means. All this means round u, round x. It's just like du dx, but we pretend that y and z are constants. So here's a function where the potential energy of the object depends on both x and y. So what's the force in the x direction and what's the force in the y direction? That's easy to find. Let's go ahead and try to do that right now. Potential energy function is equal to 4x cubed y squared plus 5y. So our question is, what is the force in the x direction if this is our potential energy function? That's simply equal to the negative of round u, looks like a 2, but it's a round d, round x. What the heck does that mean? All you got to do is just pretend that anything besides x is a constant. So if y is a constant, then y squared is just a constant. This is just a constant. So we just take the derivative as if these expressions here with y in them are just constants. That's easy then. We get, well, if this is a constant, what do we get for the derivative of 4x cubed? Well, you got to take the exponent multiplied there, so you get 12, and then you drop the exponent by 1, so 12x squared. But this is a constant here, but it's a factor, so we just keep it in there. In other words, if it were 3 there, we'd keep the 3 in there. If it was 7 there, we'd keep the 7 in there. Y squared is acting as a constant, so we just keep it in there. How about this one? Plus, what's the derivative of 5y? Well, notice, if 5y is a constant like 3 or 7, well, the derivative of a constant by itself is 0. So the derivative of this is 0. So in other words, and can't forget the negative, common mistake, we need the negative of that derivative. So our force in the x direction we have found as negative 12x squared times y squared. That's the negative partial derivative with respect to x. Similarly, if we want to find the force in the y direction, we got to take that same function and take the partial derivative negative in the y direction. So Fy will be negative round du round y. That's not a 2, it's a round d. And what will that be? Well, let's take another look at this. Here's our expression. I'll rewrite this so we don't have to look up there. It's negative round y of the expression 4x cubed y squared plus 5y. Well, it's just like taking a derivative, but we're going to pretend that this x stuff, x cubed, that's just a constant right there. We'll just pretend that's a constant. So what we get is the partial derivative, negative partial derivative is, put my negative out here, if x was just a constant, I take the derivative of 4y squared, I get 8y. That's from this and this. 4y squared, take the derivative, you get 8y. But then this constant, because it's a factor, it'll stay there. I'm x cubed. Notice I'm doing it with respect to y this time. Now, what's the derivative of 5y with respect to y? Well, that's just 5. So I get my final force in the y direction is negative 8y x cubed plus negative 5. Don't forget the negative. That's the biggest mistake you could make on that.